Yeah, we can get started. So let me introduce our speaker of today. We're happy to have Professor Swartz from Cornell University, and he's going to talk about polymatroids and finite groups for the main seminar. And this is the pre-seminar where we'll talk about some intro materials. And feel free to ask questions or about the pre-seminar, or if you cannot read the board. Yeah, and I'll help check the chat.
Yeah. So you're going to let me know if somebody has a problem, right? You're in charge of letting me know if someone wants something, because I'm not going to have a clue. Okay, so one of the very few things that I could be even confused for positive for the current situation is that I do not have to get on a plane and travel for several hours to give a talk in Seattle. So what I want to do is some intro material for this talk, Polymatroids and Finite Groups. I could have reasonably called it Polymatroids, Finite Groups, and the Combinatorial Laplacian. I won't get to that here. So what I want to do is go over some basic stuff from matroids, which conceivably everybody knows, unless I've accidentally attracted some people who are like finite groups, in which case it would be in a complete mystery. But I'm also going to cover it from the point of view of the talk, which is not the standard point of view, as you'll see. So I'm going to start, this is kind of a story. It started in 1935. Whitney wrote a paper, which is in matroid theory, quite well known because it's basically the start of matroid theory, on the abstract properties of linear dependence, where he introduced matroids. And one of his main questions answered in this paper is, what is the dual of a non-planar graph? So let me remind you what the dual of a planar graph is. If you have a planar graph embedded in the plane, so you have to actually embed it in the plane, then you get a new graph by just putting a vertex in each region that the graph divides the plane into. And for each edge of the graph, it separates two regions, so you connect with an edge there. And here we go. Now, one of the things we're going to do is so if we label the edges here like A, B, C, well, then the dual graph has exactly one edge corresponding to each edge. We'll call it A star, B star, C star, etc. If the graph is G, then we'll use G star for this, what's frequently called the geometric dual. And if I have some subset of edges, call it A, then A star corresponds to the corresponding set of edges in my dual graph, where I just star everybody, okay? So Whitney's solution to this, what is the dual of a non-planar graph, begins with the following observation. So let's let E be the edge set of my graph. And if A is a subset of edges, I want to define a rank function, R sub G of A. It can be defined in a variety of ways, but perhaps the simplest is the max cardinality of an acyclic subset of A. Okay? Acyclic, of course, means no circuits, no cycles. And what he wrote about was four properties of this. If you take an empty set of edges, well, then of course that's zero. If you have one subset of edges, subset of another set of edges, well, obviously, whatever this is, it's less than or equal to the bigger subset. And certainly, the maximum number of things in an acyclic set is certainly less than or equal to the cardinality of your set. And then something non-trivial, that if you take two subsets of edges, A and B, and add this rank, you get something greater than or equal to the rank of the intersection of those edges plus the rank of their union. So this is a normalization, this is monotonicity, this is subcardinality, and this is called submodularity, and many places in the literature it's called semi-modularity. And what he said was, well, let's call anything, any rank function on any random finite set that satisfies these four properties is called a matroid. So a matroid is a finite ground set and some rank function that satisfies these four properties. Now, the key to this whole thing is the following observation. That is, you can compute the rank function for the geometric dual from the rank function of the original graph. And the equation is, if you want to know the rank function on the dual of a set of edges that have been starred, well, that's just the rank function on the complement of your set of edges plus the cardinality of your set of edges minus the rank of all the edges. Okay? And he said, well, why don't I just use that as a formula for another rank function? So given this, given this guy, this matroid, define another rank function, let's call it R star. And now R is just any old matroid here. So ER is going to be any old matroid. We'll define ER star by this equation. We'll define R star of A. So we're going to actually define another rank function on the same set to be exactly the same thing. R of the complement minus the cardinality, plus the cardinality minus the rank of the whole thing. And the point is twofold. One, this is a matroid. It satisfies those four properties, of which only this one is not trivial. And secondly, the matroid of the dual graph is always equal to, as a matroid, the rank of this new matroid. So this thing is called the dual matroid. And so Whitney's first answer to what is the dual of a non-planar graph is, well, it's this matroid. We define this one, we take its matroid dual, and that's the dual of the graph. Okay, so we started with graphs, we ended with matroids, so our dual is something other than our original object. Our dual is some kind of abstract combinatorial rank function. But he did better than that. So I'm going to erase all this now. He sort of gave a concrete realization of RG star. So the first thing to notice is that main example of a matroid is you start with a matrix T and R by N matrix. Okay. You let E equal the columns. And you define the rank function. Remember, A is going to be some subset of E, so it's some subset of the columns of T. It's just equal to the dimension of the column space. Spanned by A. All right, and one verifies those four axioms. Three of them are trivial. And the fourth one makes a great exercise to give your linear algebra class if you want to be really depressed as to how much they understand. So this is this matroid. So this kind of matroid is called representable over F. So if the coefficients of your matrix are in the field F. So F's a field. Okay. So these are the basic matroid objects that we're going to see. Truth is that there are I don't know, somewhere between 50 and 100 equivalent definitions of matroids, where each definition allows you to recover the other definition. And usually this is not the definition used, it's the one we're going to need today. It's going to be by rank functions. Okay. So it turns out that for a graph, there's a nice matrix that gives you the same matroid. So this is best done by example. So let me bring that example back. Let me just number the vertices, 1, 2, 3, 4. You just pick random directions for your edges. It just doesn't matter what direction you pick. And you make a matrix. Okay, there's a lot of things in the chat. Should I be worried about that?
No, we're just talking about, yeah, many optional, like all equivalent definitions.
Yes, okay. Yeah, so this is, yeah, those equivalent definitions aren't going to work today, as we'll see. So there's a matrix you can make. You make the columns the vertices. And for each edge, let's call it A, B, C, D, E. Actually, I have this backwards. I'm sorry. The rows should be the vertices, and the columns should be the edges. And you just put a 1 if you're at the head, a -1 if you're at the tail, and zeros otherwise. For B, we have 3 at the head, and we have 4 at the tail, etc. And the point is that it's an exercise to show that this rank function equals the rank function of your original graph, where we identify the columns here with the edges. Okay. So the last thing I want to talk about in Whitney's original paper is that given any matrix T, so any R by N matrix let R of T equal the row space, and let S be any matrix, same coefficients, same coefficient field. Whose row space equals the orthogonal complement of R of T. Now in characteristic 0, you know perfectly well what orthogonal complement means. The weird thing is that this works in non-zero characteristic 2. What's the inner product? The inner product's the same definition. If you have an n tuple, 2 n tuples in U field F, you multiply the corresponding tuples and you add them up. If you do that, if you pick any matrix whose row space actually equals this orthogonal complement, well then magically that rank function from T, use the matroid duel, is actually the rank function for S. So now, so Whitney's paper actually for the dual of a non-planar graph, you can either say, oh, it's this matroid, which is dual to the matroid determined by the graph, or it's this matrix, something more concrete than an abstract combinatorial object. Okay. So that's our little introduction to matroids. Let me give you the one matroid invariant we're going to see a lot of, well, some of. It's called the characteristic polynomial. So let ER be a matroid. So we'll use this notation for the characteristic polynomial. It's a polynomial in lambda. It can be defined in a variety of ways. So those of you familiar with matroids would expect me now to talk about the Mobius function. I'm not going to. I'm going to give a different definition. You just take all subsets, take -1 to the cardinality, and you take lambda to the rank of the whole matroid minus the rank of your subset. And then you just add that up for all subsets. it's clearly an invariant of the matroid. And the question is it good for anything? It's fair to say that this thing is good for way too many things to make any sense. It is not possible to go over all the uses of the characteristic polynomial. Let me just give the most famous one. If you look at the characteristic polynomial of a matroid coming from a graph, so we have some graph, doesn't have to be planar, and we look at that rank function for that and its matroid. Well, if we take that characteristic polynomial and we multiply it by lambda to the number of components of G, we get the chromatic polynomial. That's the number of ways of coloring the vertices using lambda or fewer colors so that no edges share the same color. Now there's a zillion or more of these, and we will talk about one of them during the main talk, but it's hard to overstate the importance of this particular invariant. All right, for the end of this pre-seminar, I want to talk about representation theory of finite groups because it's going to appear. This is a combinatorics seminar. You may not be so familiar with it, or maybe you were familiar with it and now don't remember it. So there's a couple of things I want to talk about. So we're gonna, throughout the talk, this is going to be a finite group.
I think there's a question.
Question? Yeah.
Sorry, I was just thinking, you called the this polynomial an invariant. I was just wondering what transformations it's invariant under.
Matroid isomorphisms. And matroid isomorphism, if I came up to you and I was an alien from outer space and said, tell me the definition of matroid isomorphism or I'd blow up the Earth, I think you could save the Earth. You can,
I'm not even sure I know what a matroid is.
the only conceivable definition of a matroid isomorphism. Okay.
An isomorphism of sets that whose pre-comp and yeah, I guess just an isomorphism of sets.
Yeah, it's a bijection between the two ground sets that preserves the rank function.
Okay.
It's plural. The two different rank functions. Okay. Does that make sense?
Sure. I guess that's. I guess that seems kind of trivial as far as the
yes, it is
calling it an invariant is concerned.
The thing is that yeah, it's totally trivial. The thing is that you can have different matrices with the same matroid. So that's why we call it a matroid invariant, because you can have matrices that are not related in any obvious way that have the same matroid. So this is an invariant of a matrix also.
Oh, so is there a way to get this directly from the matrix?
Yeah. That formula. It doesn't have anything to do with the usual characteristic polynomial of a matrix. This is an unfortunate fact of life. The two have basically unrelated.
I see.
Okay. So a gamma is a finite group, and a representation, we'll probably be using rho, is a group homomorphism to GL. So today it's going to be, let me use M by M matrices with complex coefficients. Is any group homomorphism. And given two of these, let's say we have rho 1, rho 2, define the direct sum of them. So what is that? Well, if this maps into GL MC, and this one, so the same group, I want to go from the, all right, let's write this out here so you can read it. So rho 1 is going to map from gamma to GL MC, and rho 2, let's call it M1, and rho 2 will map from gamma to GL 2C. Well, then the direct sum maps gamma to GL M1, M2. See, by just making block diagonal matrices, right? That's another representation. So this would be the image of row 1. This would be the image of row 2. These would all be zeros. And row is irreducible. Well, if row is not equal to one of these things. Or any non-trivial. Of course, there's always the trivial representation. You can always take row, map it into GLMC, map everybody to the identity. Perfectly good group homomorphism, just can't be confused for interesting. It's usually called the trivial representation. And we're going to be talking about the collection of irreducible representations of a finite group. What you need to know about that is that, first of all, there's only finitely many of them. This is not entirely obvious from the definitions I've given. So everything I say is the kind of thing that you see in a first course in group representations, but you may not have had it. Or it may have been too long ago. So there's only a finite number of them. And the one thing I want to go over, and every row can always be written as a direct sum of irreducibles. And it's unique up to order, sort of. The collection of irreducible representations, let me put it that way, is determined by row. And there are two facts about it that are not completely standard, not always go over. So first of all, irreducible representations of G cross G are all of the form row 1 tensor row 2, where row 1 and row 2 are irreducible representations of G. So if you have a product of groups, representations are all this tensor product. Now, what's the tensor product of a representation? What is that? Well, that's going to map GL. Let's stick with M1 times M2 of CM1 tensor CM2. And of course, if you want to know, so this is, what is this? So row 1 tensor row 2 applied to an element of your group is equal to row 1 of this. Remember, this is a linear transformation. So I got to tell you what this does to some vector. It's in this tensor product, so it's going to be x tensor y. Well, it's this linear transformation applied to this thing. So this linear transformation applied to this guy. That's the definition. I would like you to sort of know a little bit about this for the simplest groups we got, which is Z mod PZ, P prime. Irreducible representations of P mod PZ can be identified with the group itself. As follows. Suppose I have something in here, right? So I've got something mod PZ. I need to tell you a map from Z mod PZ to GL sum MC. It turns out it's just going to go to C. It's going to go to GL1C, 1 by 1 matrices. Now, if you want a homomorphism from a cyclic group to this group, and we are thinking of this, well, it's matrices, so it's matrix multiplication. All I got to do is tell you where the generator goes. So what this map does is it takes the generator, right? It takes 1 mod P, and it goes to the complex number e to the 2 pi I over P, and then you multiply by T. So it takes a generator to e to the 2 pi I TP and does that. So there are P different representations, irreducible representations of Z mod PZ. And let me just end with combining these two facts I've given you. And that's that irreducible representations of Z mod PZ to the n are of the form, well, let's give this thing a name. Let's call this rho sub t. So it's rho sub t1 tensor, rho sub t2 tensor, tensor rho sub tn. And what we're going to be doing is we're going to, so this corresponds to elements of Z mod PZ to the n, to the tuple T1 up to Tn. So this is going to come up later. There'll be a bunch of other facts of, I'll be talking about irreducible representations. So the way to think about them is just you have these maps that can't be broken up of your group into the general linear group of C, or more generally, the general linear group of any finite C vector space. All right. So these are some of the tools that are going to come up. All right. Any questions before I'm going to bring up my slides here, I guess. I got to figure out how to make up my screen so that you can, or is that how we're going to do this? Am I going to run it from here? Okay. So let me.
Oh, actually, there'll be about 10 minutes break between.
Okay. So if anybody has any questions, yeah, okay. Go ahead.
Yeah.
While I try to figure this out.
Yeah, I do have a question about, so when we start from a graph, we constructed that matrix.
Yep.
And then we said the dual rank function is like, we can take any matrix whose rows are orthogonal in the orthogonal row space, right?
Yeah.
And then can we uniquely go back from that to a dual graph?
So different graphs can have the same matroid.
Okay.
So the answer is no. Let me give you the most extreme. Can you actually? You're still seeing the blackboard, right?
Yep.
Because I'm kind of playing with my slides here. I don't know that I'm showing you the right things. Let me give you a simple example. Like the simplest example. Let's take 3 loops. Okay. Here's the dual graph. So this thing is sometimes called a claw, right? But let's embed the loops this way. Now our dual graph is that. The graphs are different. The matrices are identical in both cases. Right? The graph of the loops is just the 0 matrix. And of course, so the orthogonal complement is everything in both cases.
So that implies that those two graphs in orange have the same matroid?
Absolutely. And they do. It may not be obvious, but it is true. They have the rank function for both of these graphs is the rank of a subset is the cardinality of the subset. Okay. So there's a theorem of Whitney that describes explicitly when 2 graphs have the same matroid. It's a little, I don't want to go into it because I'll probably state it wrong for one thing. But this is just makes it obvious that it can happen. It's just that there's other ways this can happen also. If you're familiar with graph theory, 3 connected graphs are uniquely determined by their matroid. If I hand you the matroid of a 3 connected graph, you can write down the graph up to isomorphic.
Oh, I guess that would be true that all trees would have the same
That's
with the
right.
same number of edges, or all forests, I guess, would have the same number of
Yeah,
with the same number of
So there's
edges.
lots of things. So like if you want to study the structure of trees, don't use matroids. you're at least don't use this matroid. There are actually other matroids associated to graphs that people have invented that can distinguish them. But certainly the standard, this is called a cycle matroid. This was Whitney's original idea. Don't use that. It won't help you at all.
Okay, are there any other questions? Well, then let's all thank the speaker for the nice first seminar. It was a great board work. It's me. Okay, feel free to add that clapping reaction.